Hi class, this is Mr. Morris. Today we're talking about rate laws. It's an important topic in kinetics. First we talk about differential rate law. That's what we're going to focus on today. It's usually just called the rate law. It shows how rate depends on concentration. And when we talk about rate, we're talking about how quickly a reaction takes place. So it's referring to how the rate is affected by concentration. Then in our next set of notes, we're going to talk about integrated rate law. That shows how concentration depends on time, and we'll go into more detail about that in our next set of notes. We've got this general form for rate law with one reactant. So if we've only got one reactant, let's say it's a decomposition reaction, you would have a rate law that looks like this. It's going to be rate equals K times the concentration of A to the N, where A would be the reactant, and then N is some number, and we don't really know what it is unless we do some experiments. The general form of the rate law with two reactants is rate equals K times A to the N times B to the M, and these brackets mean concentration. So what these both indicate is that when the concentration increases, usually the rate increases, and vice versa. The opposite's also true. Rate is given in molarity per second or moles per liter second. So it's the concentration changing over time. The brackets mean concentration in molarity or moles per liter. Molarity and moles per liter mean the same thing. And K is the rate constant. It has various units that are specific for each reaction. The K value, that rate constant, accounts for all the factors that affect reaction rate besides concentration. So things like surface area, proper orientation, activation energy, temperature, and so on. Now this equation we're going to get into more later, but I wanted to give you a brief introduction to it. It's called the Arrhenius equation, but this value of K that we're solving for in the Arrhenius equation is the rate constant. Again, we'll go into more detail with this later when it's more important, but I want to talk to you about what it is because it shows us some of the factors that make K significant. So first of all, the surface area, states of matter, and so on are accounted for in this factor that you see, the uppercase A. E, the lowercase e, is Euler's number. It's the little e on your calculator. R, you know, is the gas constant, but we're talking about the gas constant in specific units, 8.314 joules per mole Kelvin. And then temperature has to be in Kelvin. And this EA, that's activation energy, which we will discuss in more detail later. All right, so as we discussed a little bit ago, rate is equal to K times the concentration of A to the N times the concentration of B to the M if we're talking about two different reactants. So let's talk about what these numbers mean. I've highlighted N and M because that's what I'm focusing on this part of the notes. N or M, or both, are the reaction order. It could be an integer or a fraction. Now the possibility you'll be seeing in this course, especially on the exams, is going to be 0 or 1 or 2. If n equals 0, the reaction is what we call 0 or 0th order. You'll see that sometimes where you have the number 0 with a little th, 0th. The rate is independent of concentration in this case. Rate equals K times A to the 0, where N would be 0 in this case. Now remember that anything to the power of 0 equals 1. That's a fact you want to make sure that you're aware of if you didn't already know it or if you'd forgotten it. That's an important fact to know. Anything raised to the 0 power is 1. So what that means is in a 0 order reaction, the rate is just K. K times 1 is just K. Now if N equals 1, so if our reaction order is 1, the reaction's first order, the rate is directly proportional to concentration. So rate will be K times the concentration of A to the 1 power, or in other words, K times the concentration of A. If n equals 2, we say the reaction is second order, and the rate is proportional to the square of the concentration. Rate equals K times A squared. The rate constant in reaction order can only be determined experimentally. We can't just look at a balanced equation to determine it. That's not going to work. The reaction order determination can be determined through an observation method, or through a mathematical method, and we'll talk about both of those. All right, let's look at an example here. I want to determine the rate law of this experiment. I've got a reactant A, okay, and I've got my rate at different concentrations. I have 3 different experiments. One experiment has 0.10 molar concentration. The second one has 0.20 molar concentration, and the third has 0.40 molar concentration. I've numbered these, and it's often a good idea to go ahead and number your trials because it makes it a little easier to follow along. The reaction order for A is blank because so on. That's what we want to do. We want to write down what's the reaction order for A. So I would start by just leaving that blank there. This is a good technique when you're answering FRQs like this one too. And there would be a more direct question on the FRQ, but you want to write down the reaction order for A is, and then leave a spot for it, and then we're going to use our justification. So you notice that if I go from 0.1 to 0.2, so trial 1 to trial 2, I've doubled the concentration and the rate is still the same. So when A is changed, the rate stays the same. The rate is independent of the concentration. So rate law, because it's independent of the concentration, that means it's just equal to K. It does not matter how much the concentration is. Rate equals K times A to the 0, or rate equals K. It's really easy to figure out what K is now because it's just the rate. So the rate is 0.015 molar per second. So K is 0.015 molar per second. Keep in mind the K units for a 0 order reaction will be molar per second, moles per liter second, or moles times inverse liters and inverse seconds. These all mean the same thing. They're just different ways of writing it, and you want to get used to all of those. You'll see them in one of those forms or all of those forms on tests. Let's look at another example. With this example, I'm going to go through a descriptive method and an algebraic method, and you can decide which one you like better. Both of these are acceptable ways to answer the question. I want to write the rate law for example 2. That's my ultimate goal. First, number your trials 1, 2, and 3. And as I go from trial 1 to 2, I have doubled the concentration. And I could go from trial 1 to 2, 1 to 3, 2 to 3. It really doesn't matter in this case which 2 trials I pick. I just need to show a change. And remember, our general rate law is rate equals K times the concentration of A, which is our reactant, to the N power. And we're trying to figure out what N is first. So going from experiment 1 to experiment 2, the concentration is doubled. The rate is also doubled. The concentration of A is doubled and the rate is doubled. So what that tells me is they're changing by the same factor. There's a direct relationship. Rate and the concentration of A are directly proportional. Because of that, we know that this has to be first order for A. And our rate law would just be K times A to the 1. Here's another way to get to the same answer if I wanted to use the algebraic method. I'm going to use this expression, rate equals k times a to the n, and I'm going to plug numbers in. But I'm going to compare to the two different rates, the two different concentrations. I need to make a proportion, I need to make a ratio of the two. So I have rate 1 over rate 2 equals k times 0.10 to the n power over k times 0.20 to the n power. So what I've done is I've got my initial rate, rate 1 over rate 2, equals the rate constant times the concentration from trial 1 to the n power over k times the concentration from trial 2 to the n power. And we're going to solve for this. There's a couple things that I can do to try to make my life a little bit easier. First of all, we'll plug in these numbers. Rate 1 is 0.015, rate 2 is 0.030. I can also cancel out those k's because it's the same reaction. Okay, so I get here, and 0.015 over 0.030 is going to be 1/2 or 0.5. 0.1 over 0.2 is 1/2 or 0.5, but I have to keep that exponent to the n power. So 0.50 equals 0.50 to the n power. So what would n have to be to make this statement true? Well, it would have to be 1, because 0.5 equals 0.5. So it has to be to the first power. 1 equals n. So this is the algebraic method to prove that the reaction is first order for A. All right, now we need to find our rate constant. I wanted to determine the rate constant, which is this value k right there. I'm going to use experiment 2. I could use experiment 1 or experiment 3. It doesn't matter as long as you're consistent. So rate equals k times a to the 1, because this is first order reaction, which is also another way of saying k times a. So all I have to do is plug in my numbers. Rate is 0.030 for experiment 2, and it's 0.020, that's the concentration of A for experiment 2. So I've just plugged my numbers in. 0.030 equals k times 0.20. Now I'm going to divide 0.030 molar per second, and I'm just plugging in units because we need to also know our units. Molars per second over 0.20 molar. Got to plug in those units. And then we're going to cancel out whatever we can. I can cancel out the molarity, and now I've got inverse seconds. 0.03 over 0.2 is 0.015, and it's 1 over seconds. Or you could write this as inverse seconds, s to the negative 1. Those units are equivalent. So rate equals Ka to the 1, or rate equals K times the concentration of A, and K is 0.015 inverse seconds. K units for first order reactions are going to be 1 over S, or S to the negative 1 inverse seconds. These units are equivalent. All right, let's do another one. Example 3. 0.10, 0.20, 0.40 are my 3 different trials. I've got trial 1, 2, and 3. We'll start by writing our rate law. Just a reminder, rate equals K times the concentration of A to the N, and we want to find out what N is, and we want to find out what K is. We'll start with the descriptive method. I'm going to use experiment 1 and experiment 2 again because they look pretty easy to deal with to me. The concentration of A is doubled. I went from 0.1 to 0.2. And the concentration of, or not the concentration, the rate is quadrupled. So if I look at the rate, 0.015 goes into 0.060 4 times, and I could think about that in terms of 30s. 0.015 doubled would be 0.030, doubled again, that would be 4 times to get to 0.060. Okay. So if when I double this is quadrupled, that tells me that rate is directly proportional to the square of concentration, or to A squared. So I doubled it, it went up by 4. Well, 2 squared is 4, so that tells me my order has to be 2. The reaction is second order for A. That's the verbal way of explaining it. Now let's look at the algebraic method. Looking again at experiments 1 and 2. All right, I'm going to start with my rates for experiments 1 and 2 are equal to K times concentration for experiments 1 and 2. Remember, we're going to be making fractions out of those to the n power. So rate 1 over rate 2 equals K times the concentration of 0.10 molar to the n over K times 0.20 molar to the n. All right. And I've just plugged in those rates. Again, my K's canceled out, so I've gotten rid of those in the second step. When you divide that out, you're going to get 0.25 equals 0.50 to the n. I want to go ahead and mention real quick, it's a good idea, it's good practice with these notes to try to get used to doing some mental math. I know that this stuff does not seem like it's immediately apparent, but it's important to try to get used to doing mental math, because you will see some problems like this in the multiple choice section which you cannot use a calculator on. All right, so 0.15 goes into 0.015 goes into 0.0604 times, so that's 1/4, which is 0.25. This is 1/2, which is 0.5, and that's to the n. All right, 0.5 to the n, and then I've got 0.25. Well, what if I squared 0.5? 0.5 squared is 0.25, so n equals 2. The reaction is second order for concentration of A. And again, I canceled out those units. Okay, let's use experiment 1 in order to find the rate constant. So we know that the rate constant is, or we know that our rate law is K times the concentration of A squared. So we'll just plug stuff in for experiment 1 in this case. Rate equals Ka squared. We have 0.015 is our rate, 0.015 molar per second, equals K times 0.010 molar squared. Now I'm going to divide to solve for that. K equals 0.015 molar per second divided by 0.010 molar squared. And I got that 0.010 molar squared by squaring this number. 0.1 times 0.1 is 0.01. All right, so I notice that I can cancel out one of those molarities, and I would just have one molarity in the denominator. Or you can think of it this way: when you're dividing numbers with exponents, you subtract the exponents. So for molarity, we're going to do 1. Up here we've got molarity to the 1, or just molarity, divided by molarity squared. So 1 minus 2 gives us -1. So we end up with molarity to the -1 times seconds to the -1, because seconds are in the denominator. Rate equals Ka squared, and 1.5 inverse molar and inverse seconds. That's the units that we're going to have for a second order reaction. So second order reactions are going to have units of inverse molarity times inverse seconds, or 1 over molarity times seconds. Those units are equivalent.